And today's lecture is going to be on CPU scheduling. I'm going to review a little bit of the concepts that I started last time, and then we will go through the algorithms. So today's all about the algorithms, but it's kind of weird to start in the middle of a lecture, so I'm going to not spend as much time, but go over concepts and stuff so that you have a background in what it is we're talking about here in terms of CPU scheduling. So this is chapter 5 of the textbook, if you have the textbook, and it's on basic concepts of CPU scheduling, the algorithms, their criteria, and I believe we stopped on the criteria. You're going to need this lecture for your assignment, one of your assignments that does a CPU scheduler. You're going to compare two schedulers, so you're going to need to know what the basics are. In your comparison, you're not actually writing a scheduler, you're writing a demonstration of a scheduler. So you'll be essentially implementing a simulation or demonstration to show the concepts. So we'll look at scheduling criteria, scheduling algorithms, multiprocessor scheduling, and things associated with that. Can we keep the volume down? I'm sorry, I just don't want to yell. All right, I feel like I had to talk over you. Okay, basic concepts, and then the people in the back can't hear anything. So, basic concepts. We want to maximize the CPU utilization obtained with multi-programming. So we want to make the CPU work constantly. And what we're trying to do is manage the CPU bursts and the I/O bursts. And I/O and CPU run simultaneously. So we can have both of those two working. We have separate queues for the different jobs, and the jobs are what we're scheduling. The jobs are like processes. But one job might contain multiple processes depending upon the mapping, and we'll get into CPU thread map. Well, we'll get into mapping as we get into process synchronization. So, but long story short, we have a cycle of CPU execution and then I/O waiting, and we're micromanaging the cycle between the I/O and the CPU to maximize the CPU utilization, make the jobs run as fast as possible. And then we introduce things that slow it down. And the things that we're going to introduce are in form of the algorithms. So when we compare the algorithms in a few minutes, think about, one is a compromise to the other. One of them does something good with this, another one does something good with that. But there's no algorithm that does everything. So if you can invent a CPU algorithm, then you could get maybe a PhD in computer science, invent a new CPU algorithm, and then you could probably retire, hopefully one of these days, who knows. So we're looking at CPU burst distributions as well as a concept, looking at the alternating sequence of CPU and I/O bursts that occur. And just to keep in mind that it's a constant juggle. We've seen this slide actually, so I'm going to kind of go ahead. And we've looked at the histogram of CPU burst times with burst duration, which is how much time is the process getting from the CPU at each one of the times it gets to visit the CPU. And then usually at this point students start thinking, well, why are we worried about any of this? Well, because we can't just run one process till it finishes and then run another process till it finishes, which would be the perfect way of scheduling stuff. And it's called batch processing, by the way. And then when one finishes, the next one starts, but then there's wait time if we do that. It doesn't give us a user experience. So to create the multi-threaded user program experience, we have to juggle the burst times and the frequencies, how often a process is getting CPU time, and how much time are they getting when they get it, and then come up with a unique combination to meet all the criteria. So the CPU scheduler, what does that do? Well, all of these algorithms we're going to look at are going to do the same thing, and they're doing this. They're selecting among processes that are already loaded in memory. Nothing that hasn't been started yet, just stuff that's been started that is designated as being ready. So we remember the process states. So just because it was created doesn't necessarily mean it's ready. Might be running. So it's just juggling the readies to execute and allocate the CPU time to get it out of the system. So we start the process. CPU scheduler wants to get rid of it. Wants to run it till it's over with and then take it out and then run something else. But it has to run multiple things at the same time. So CPU scheduler's decisions take place. Switches from running to waiting state. So a process state changes by the CPU scheduler. So the processes get loaded up into what's called a process control block, or PCB. And inside the process control block, the state gets updated along with how much processing has happened so far, where in the program counter we're at, what's going on essentially throughout the life of that process. So it switches, and then it goes from running to ready, and then switches from waiting to ready, and then it terminates hopefully eventually. So scheduling under 1 and 4 is non-preemptive, and then we have scheduling that is all other scheduling that's preemptive. Preemptive means we're going to stop it. Non-preemptive means it's going to run until it finishes what it's doing, and then we're not going to interrupt it in itself. Which means that most of the I/O jobs that run are not preemptive. We're not going to break it because there's more overhead and there's more work in having to take that process and save its state and restart it, and basically kind of figure out how we're gonna manage it. There's more overhead in context switching and management than there is just to let it run. So these overhead that I keep talking about, or have just mentioned it myself, is usually referred to as context switching. But context switching is really supposed to be defined by the term where a CPU scheduler decides to start a process, stop it, put it back into the queue, pull another one out of the queue, start that one, stop it. So the time wasted in between this process running and that process running is context switching. We also have other things of memory access speeds, other factors that play into the speed of this processing, how much available cache is there, how much memory is available, what speed is the memory running at. All these little factors come into place. The dispatcher is the one who's deciding who's going to run and who's going to stop. So it gives control to the CPU to process the selected by the short-term scheduler, which is going to be your short-term queue. So remember short-term, medium queue, long-term, short-term, medium, and long-term queues. So all processes have to get CPU time. So they go to this, we create what's called a short-term queue or short-term scheduler that basically all processes have to go through. It's short because you're only getting a couple of CPU bursts, that's all you need. And once you get your CPU burst, it's like visiting the traffic cop, but then you go to your I/O queue or you go to another queue. Most requests are I/O related. That's what we're doing with our computers. We're using a CD-ROM drive, or using the disk, or using the memory. That's all I/O actually. So how much time does it really need at the CPU? Probably not that much time. And we don't want it to stay in that queue forever because it'll never get CPU time if it doesn't. So we make it short term, short bursts, then we swap it to a long term. Long-term queues are I/O bound processes that are waiting for non-preemptive jobs usually, which is longer wait time, longer CPU burst time in general. So we configure the different queues. We have a dispatcher that works with it. The dispatcher juggles the processes between all these different queues essentially. So jumping from to the proper location in the user program, restarting the program, switching to user mode from kernel mode. Remember the dual mode processing that I talked about in the first week of class. So we also have, instead of context switching, we have another term called dispatch latency, which is another time-consuming part that's wasted. I shouldn't say wasted time. It's just another factor that's put in. It's the time it takes for the dispatcher to stop one process and start another one. It's referred to as dispatch latency. So we stopped, well actually we covered this stuff as well, and I covered the assignment description as well. This is what you're using. This is the scheduling criteria that is mentioned in the assignment description that we have on CPU scheduling. And it's going to have you compare multiple, well you have to create them, multiple meaning at least two. So implement two schedulers that can be the same program, or they can be two separate programs. So if I were doing it, I just have like one program with two options. Do you want to run this one or do you want to run that one? Or maybe actually, without even having any options, its purpose, the program's purpose is to run the two schedulers. So it could just run number one, run number two, and then show you the output. And the output is this stuff here. The output is between scheduler A and scheduler B, what's the CPU utilization of both? And that CPU utilization is keeping it busy. This one was able, in 5 minutes, this one, or 4 minutes or 5 ticks or whatever your counter is going to be. This one was able to process 10, this one processed 9 or something. Because maybe it was spread out, but maybe they're both going to process the same amount. There's a bit of overlap with all of these different criterias. So you sort of have to read into it and define what you're measuring. So just to say CPU utilization, how are you going to measure that? Which is actually kind of interesting because then you take real life CPU schedulers and you look at their CPU utilization. Well, they all look the same really from a marketing perspective. You're not going to say mine's really bad. They're all going to pretty much be 100% utilization. So sometimes people put it in percentage. You might not necessarily get any variance between the two schedulers you're going to create unless you make it yourself. So you can play around with the data. And I'm going to show you how to do that when we look at the algorithms in a few minutes. Fake the data to get the results you're looking for. To prove your demonstration. It's a demonstration. It's a simulation. You're not actually implementing these in real life, essentially. So if one works better with longer jobs or shorter jobs, we'll give the one that works better with the shorter, give them the longer jobs, and then switch it around. Then you'll see where they make mistakes. Or actually, it's not mistakes, where one of them is slower or faster than the other. When we get to the algorithms, you'll see what I'm talking about. Also throughput, which is the number of processes that are completed, that complete their execution per time unit, which is basically throughput is going to essentially be how much context switching or dispatch or latency are you talking about. Yeah, the more you put into there, one of them might have more than the other, which means the throughput's going to be different in the end. Turnaround time, the amount of time to execute a particular process from start to end, given all, and that's going to be a factor of how much time did the process take. Was supposed to take, how much time did it really take, and what's the average time for all the processors. We have some short processes, some long processes. You put them all in the same, maybe it depends on the order of the processes, maybe it depends on, I don't know, how much latency there is in the switching, how often you're switching between the processes or something, or how big you make your CPU bursts. And we're going to go through all that stuff in a few minutes, but the turnaround time is going to be different than how much time it actually does take. Also, waiting time is another factor. So the amount of time, that was probably an easy one to calculate. How much time does the process have to wait for CPU time? So how much of it's waiting? And all these numbers here, you're going to come up with your own math for. You're going to figure out, well, waiting time is going to be the amount of time minus the throughput time or something, or, you know, and you're going to figure out how to do it. And then response time, that's going to be a hard one to measure because it depends on how you set it up. So the amount of time it takes from when a request was submitted until the first one is produced, your first response is produced, no output for time sharing environment. So if you wanted to, you could put like a random, you know, use a random and then start the jobs at randomly different times or something, and then you'd have different stuff in there. So optimization criteria, we want to maximize the CPU utilization, as I previously mentioned. We want to maximize the throughput, get as much done as possible, minimize the turnaround time, how long it takes, minimize the waiting time, and minimize the response time. As soon as we click on that program, we want it to run. So let's take a look and see what we're talking about here. This one's called the first come, first serve scheduler. In a first come, first serve environment, what we're looking at here is process number 1, process number 2, and process number 3 over here. And the columns in this PowerPoint, well, this is PowerPoint, brought it up in preview. So this is the 24 is the burst time. It's supposed to be here, but it didn't line up right. And 3 and 3. So suppose the processes arrive in this order. Process number 1, process number 2, and process number 3, which means they arrived in order. What does that mean? You double-clicked on Word, you double-clicked on PowerPoint, you double-clicked on Excel. And they arrived into the queue. What did I say? Word, PowerPoint, Excel. They arrived in that order. So here's a Gantt Charts. Don't worry about it if you don't understand what Gantt Charts is. It's a project management kind of term, where it shows you that P1 arrived first, P2 arrived second, P3 arrived third. So the wait times for P1, and there's a little bit of weirdness here, it just says waiting time. It's wrapping actually. So we got P1 had to be 0, because it just started immediately because it arrived first. P2 had to wait for P1 first time at 24, so it started at, this is 25 underneath this mess of stuff here, or excuse me, 24 at this mess of stuff. Because it starts at 24, which is the end of P1, and then so we have 3 and 3. So 24, 26, 27, 27 to 30. So we have 3 and 3. So the average wait time turns out to be 17. We add up all the wait times and we divide by 3. This is because the biggest one, this is first come, first serve, which means it's just going to take it in the order that it arrives and it's going to run it till it's done. So process, and you can actually do this one, it's pretty easy to implement. And so it took 24.33 by the time it ended. So suppose the processes arrived in a different order, like the first come first serve algorithm, but P1 came in late, came in the last order, so P2, P3, and then P1. So then we have different average wait time. It's now 3 instead of 17, because the 2 short guys didn't have to wait for the long one to finish first. So the Gantt chart here looks like this. We have 3 minutes, or 3 clicks, and then 24. Probably a better way of doing it, right? So the waiting time here is 6, 2, 0, and 3. So the average waiting time is 3, much better than the previous case. It's the Convoy Effect, where short processes are behind the long processes. So even though this guy only takes 3 minutes, because he's got to wait 24, I'm just going to call it minutes. We'll just call it, or seconds, microseconds or something. It's really quantum, or clock ticks, I should say, or burst times. So anyway, he's got to wait 24. I'm not going to get done until 27. See, so his throughput time, his burst requirement was 3, but his actual time was 27. Which means that's kind of slow. But here now we have 3, 3. Put those first. So if you're going to design a first come first serve algorithm, you got to make sure that your short jobs arrive first and your long jobs arrive second or third, and then your long job is going to wait for the little guys, but it's a shorter wait time overall because it's the longest one. So you have a real-time system where things are running, and basically what ends up happening then at this point is you got 3, you got 24. They all came, and then we got one that comes in, it's 95 or something. Or it goes, something new gets entered into the system. And the problem is people go, oh, well, we'll just reorder this, right? You got to check for the reorder constantly. Or on each new job that gets put into the queue that slows down everybody. Because now you got to reorder. And what if one of the jobs is already running? What if this first one was 24 and the next one was 3? And you go, wait a minute, stop the 24, start the 3. Context switching time. So the problem with this is we don't know what order the jobs are going to show up in. And if we do it, and we're going to try and organize it on the fly, we have overhead in reordering the queue. So we can put the shortest jobs first, which, would be ideal in the situation. So this is the first come, first serve scheduling algorithm. Here's some more analysis of it. It says it's associated with each process. So associate with each process the length of its next CPU burst. Use those lengths to schedule the processes with the shortest time. 2 schemes. Non-preemptive. Well, in a non-preemptive scheme here, you're not going to stop the process. And a new shorter one just showed up. So if you have a job running and all of the new shorter ones just keep showing up, the job's never going to run. Because you're going to stop it, stop it, stop it, start, new one, stop, 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 stop. If we did this with a printer, we'd end up in a bad situation. Because the job would never print, essentially. But how often does that happen? See, usually printers use first come, first serve. The first item that comes into the queue is processed first. And so if there's a big long job in there, you got to wait. So it depends on how many jobs are ahead of you and how long they are in terms of how long it's going to take for your job to be printed out. So, is there a problem with the door? No, he just wants to sit in the back. Okay. Is there a seat back there? Well, there's a chair. All right. That's like the furthest space you could possibly get in this room. All right, so non-preemptive, once the CPU is given to the process, it cannot be preempted until it completes all its CPU bursts. Or you can use a preemptive scheme if the new process arrives with a CPU burst length that's less than the remaining time currently on the executing process. Well, that's an expensive algorithm. Because you got something running, you got to stop the running. Because imagine all the context switching is happening. There's no CPU activity going on while that's going on. So you're going to stop the CPU, say, okay, how much time you got left? Okay, wait. You know, all that time wasted, it could have just finished the job, essentially. So then this scheme is known as the shortest remaining time first. So this is a different algorithm that people have tried. And imagine people, operating system vendors have tried all of these different combinations and still hasn't been perfected yet. So for shortest job first, which is what this stands for here, shortest job first, SJF, is optimal. Gives minimum average wait time for a given set of processes given the order. So it's very order driven. So here's an example of a non-preemptive shortest job first, where we're looking at now, instead of just the process and the burst time, we're looking at the arrival time. So we have first come, first serve, that's the first one. Shortest job first, that's the second one we're looking at. So you could take first come, first serve and compare it with shortest job first if you want to in your assignment. So, and you'll see we can do longest job first, shortest job first, first come, first serve, preemptive, first come, first serve, shortest job first, preemptive, shortest job first, non-preemptive. So you can pick any, those are all different algorithms, by the way, so you can pick any two combinations. So now you know how to make your job easier if you want to. So now we're going to add arrival time to this, and here's the thing. So depending upon the algorithm you pick, you're going to have to determine what kind of input you're going to put into it. This does not have to be like a file that you read in and parse it out. And you can just hard set it. What I mean by hard set it, do something like this. We have 4 processes. We have different arrival times and we have different burst times. So in the shortest job first, non-preemptive, and they arrived in this order, well, isn't that going to be kind of like the first come, first serve kind of, because the 7 arrived first, arrived at 0, and then we have the 4, the 1, and the 4 that arrived in next. So if we have the average wait time here, the calculation's messed up, but it's actually 4 instead of 3, which was the better one, actually, when they ordered them differently. But this is non-preemptive, so we're not going to switch the order around. So this is just taking the 0 to the 6, because it has to wait for 6, and then plus the 3, plus the 7, plus the 8 divided by the 4. So the preemptive model, if you load this up in PowerPoint, you'll see this non-skull wrapped like this. It's kind of odd here. So the example of the non-preemptive shortest job first, the preemptive shortest job first. Now you see that the average wait time in this particular example, I believe, is 11. No, it's 3. It is 3, so it made it shorter, because this line here is actually showing, and this is showing the 0 time to 2 to 4 to 5 to 7 to 11, which is going to be the calculations that are of the arrival order. So we have the arrival time, we have the burst time to consider. Same kind of way of scheduling it with the with the first come, first serve. This is the same Gantt chart layout. So if you're confused and you don't have the PowerPoint in front of you and you're looking at this, imagine we're just calculating the wait time and we're dividing it out by the number of processes, which is 4 in this particular case. So we end up with a 3, which is a little bit better on the preemptive side. However, it depends on what kind of jobs these are. As I was mentioning before, you may not necessarily want to preempt a job. It actually might even cause corruption in some cases. So determining the length of the CPU burst. So you can only estimate the length. So it can be done using the length of the previous CPU burst, using exponential averaging. Because let's talk about CPU burst as an example here. Here we're taking the burst time that's needed and we're just running it completely through. So we have other algorithms that give everybody the same amount. So if we have 4, we do like what's called a round robin, which I'm going to get to in a few minutes. And we put the CPU burst at 2. or actually we'd probably take it at the average. Actually we'd probably take it at the highest, so you get the most jobs to complete on the first time through, which is another scheme of doing it this way. So if I said 4, so process 1 needs 7, it would get 4, it would have 3 left over. It'd be put back into the queue. But the next process 2 would get 4 and it would go out of the queue. And the next one we have 4 wasted bursts. It only needed 1. We have 3 wasted bursts because it only needed 1, but we're going to give it 3 more. So the CPU just sits there for 3. Doesn't do anything for 3. So we wasted time there. And then we have 4 that was done and completed. But if we made it 3 instead of 4, this job would go back into the queue. We'd have 1 less wasted minute here, click here, and then we'd have this one would go back in the queue. Every time it's got to go back to the queue and come back out to get more time, it takes longer. So looking at not using the burst time that's required, and coming up with an average or coming up with the highest or the lowest, and using that as a factor determines basically how much wait time some of the other processes are going to suffer from. So you can calculate the average, or using the actual you can calculate the average. This algorithm here is actually using the previous one, which is in this particular case not so optimal because the biggest job was first. So the previous wait time, well, CPU burst is going to be too big. So predicting the length of the next one, here's a little average here with time, the CPU bursts that go on. If you do it as a factor, you can kind of balance it out to give the right amount of CPU time for each one of the processes that's in the queue if you're using an averaging. So we have exponential averaging that can be done as well. You don't have to do any of this for your CPU algorithms. For your CPU algorithm, you can just use the actual burst times that are needed if you wanted to. I'm actually not going to go over the exponential averaging either, because this really isn't done anymore. Because here's the problem. If you're going to figure an average, then how often are you going to do this? Because this is a real-time situation. If it wasn't real-time, if you just turned on your computer and just, okay, I want to run this, this, and this. And then this is what I'm going to run, and then I'm going to shut my computer off. Again, if the computer actually knew that, then it can come up with an average. But unfortunately, new stuff gets put into the queue constantly. It's live. So if you're constantly doing this is computational time. You're constantly figuring, what's the average now? What's the average now? What's the average now? You're wasting so much time coming up with the averages that if you just didn't use the actual times and you just basically just took it and just ran everything, it'd run faster. Or, it'd probably run as fast as the first come, first serve. So if you want to do a simple comparison where one algorithm is going to run significantly slower than the average, just keep doing averaging every two clicks. And you've introduced a bottleneck, essentially. It's that averaging that's just going to take too long. So it's kind of like deadlock avoidance. When you put deadlock avoidance into an operating system, you cause latency, because you cause time that the operating system is trying to figure out, is this okay to do? I want to try to avoid deadlock. Is this all right to do? When you could have just, ran things faster if you didn't care about deadlock, and then later on, if something happens, recover from it. Or just put up a blue screen of death or something and just recover and walk away from it. So, just like queues that we have in print queues, we can put priorities. So if we do a first come, first serve as an example, and the boss puts a job into because most print queues are first come, first serve, but the boss wants to print a job out. He has a higher priority, higher status. So his job will preempt everybody else's jobs. will end up being the first into the queue. So priority scheduling could add starvation to another employee's print job. All the bosses are printing out annual reports. It's Monday morning. They're just going to print out everything completely. And then nobody else is going to have anything print out till Tuesday or something, which is one of the problems with this. But it's a priority scheduling, which says if the operating system has a job, and that's more important than the user mode jobs, then we're going to run that one first, which is what Unix does actually. But instead they have two queues, or they have multiple queues instead of putting it all into one queue. And then you have to put on some sort of a aging solution to it. So if you age the items, if employee XYZ, whatever, has a job in from 10 o'clock in the morning, maybe by noon, if it's not printed out yet, it'll say, hey, I've been waiting since 10. Then the next person will come in. Okay, pull out one of those waiting processes and run it. And then we'll delay the higher priority processes. So that's another scheme you could possibly implement if you want to. So a priority number or integers associated with each process. And that's our grouping of process IDs in Unix and Linux, actually. So numbers past a certain point are of user mode priority. Everything below that numbering scheme is kernel mode priority. And then we can assign different process orders and numbering systems to different users as well. We can keep track of all that stuff if we're going to do that. And then we're going to end up being able to come up with different types of queues as well. So we can have a multiple processing priority queues for different process priorities. So we have all the users go into one queue, the kernel goes into another queue, and then we can put different priorities on the different queues. And then we have modern day scheduling, which goes on essentially. Most of the schedulers these days that are implemented in real life operating systems are using multi-queued, tiered. So if you've got a queue, you can put any algorithm you want on it. So we can put a more efficient algorithm on a higher priority queue. As an example, we can run a round robin on a higher priority, put a first come first serve on a lower priority. Basically experiment with different algorithms for different queues, and then run the queues in different orders, depending upon what's going on. And we can calculate aging in there, and then everything can run smoothly. So it's a little bit more complicated than applying a single algorithm when you're implementing. And that's why I said you're running a demonstration, a simulation. Not that you're really scheduling any jobs. That would be, you could write one, but you're simulating it. So the CPU is allocated to the process with the highest priority, smallest integer, highest priority. So 0 is the shell. Anything below is going to be the highest priority. So user mode is always lower priority. We can have a preemptive or non-preemptive status assigned to the priorities, especially if we multi-tier it, multi-queue it. We can have one queue that preempts, the other queue doesn't preempt, stuff like that, depending upon the nature of the queue. Shortest job first is a priority scheduling, where priority is the predicted next CPU burst time. Problem you might have is starvation, where lower level processes may never execute because there are too many higher priorities out there. And then the aging, as that time progresses, the priority of the process could actually be upgraded, and then all of a sudden a low priority process turns into a high one because it's sat there all morning and it needs to run now. So round robin is another scheduling algorithm that can be used, and I mentioned it actually already, but each process gets a small unit of CPU time called a time quantum. So the time quantum is how much time are we artificially going to give to a process. We can base it on an average, but then, everything I said about averaging, probably not so good, or we can hard set it, or we can adjust average or weighted average. So once a day, I don't know, once an hour, come up with the average if we want to, or just hard set the average, depending upon the nature of jobs. So we have different queues set up, and we have one job that has low frequency. We don't have to average it. We can just do a round robin on it maybe, and then just figure out a time quantum that's suitable. So usually 10 to 100 milliseconds. After the time has elapsed, the process is preempted and added to the end of the ready queue. So there are no processes, or if there are n processes in the ready queue, and the time quantum is q, and you can come up with these variables on your own. You can set the number of processes, the quantum time, and each process gets 1 divided by n of the CPU time in chunks. So of at most q times. So if everyone gets 4, then everyone's going to get 4. You only need 1, and you got 3 left over. So you can probably imagine that there's introduction of wasted time, and then there's swapping that goes on. So no process waits more than n minus 1 divided, well, n minus 1 q time units. So So the performance at queue is large would use a first in, first out. If the queue is small, then the queue, the time, quantum time, must be large with respect to the context switching, otherwise the overhead is too high. You have to make it big enough. Because it's like, you know, if you have 4 jobs, and the 4 jobs take 10, and you give them all 2, then you got 5 times they got to go in and out. If you gave them all 10, then they only got 1 time they go in and out of the queue. And they're done after the first time that they go and they get CPU time. But then the average wait time is going to be higher because the response time is going to be lower with a smaller quantum. So if they take 10, but they're only allowed 2, everybody's responsive within 2. So at the most you're waiting is 8, because you have 4. If you have 4 jobs in there, you're waiting 8. If you're the longest wait time, the longest response time is 8, but you have a higher wait time because you're back into the queue, back into the queue, back into waiting for somebody else. So the wait time goes up. So that's why I was saying at the beginning of this lecture, you have to kind of rig your input with your technique to come up with your comparison. So you can have one that, one way of doing it that has a faster response time. That's your sales pitch, but the wait time is going to be astronomical. It's going to be not worth it if the quantum's not set right. But maybe we can spend time and do an average quantum and figure out, well, if it's 10, and we can give it all 10, and we know that information, then we can give it all 10, then we have slower response time but faster wait, less wait, so not as much wait time, but slower response time. Do we really matter if we don't get that much response time if when it runs, it runs? So imagine what happens with Windows. There's a long response time actually. You click on it, it might wait. That's response time. The time it takes for you to actually get a GUI to show up. But when it shows up, quick. No faster turnaround time actually. So. Or if you're an operating system and you're loading stuff, you can preload stuff at a lower priority, which is actually kind of interesting. Because if you're talking about, what we're trying to do is maximize the user's experience, or improve the user's experience, give them the illusion that everything is running simultaneously. And then you have to kind of think about, well, then if everything is running simultaneously, not everything is running at the same time. So how are you going to make it appear? So if you get a graphics processor on there, and you take all the graphic work, give it to the processor. The graphics is working simultaneously with the CPU. So sometimes the GUI comes up. The user's just going to sit there for a few minutes. Oh, I see it running. If the GUI comes up instantly, which is why a GPU makes your system always feel more responsive. It's really probably running at the same speed as your CPU is capable of, but the GUI comes up and you say, oh, it's loaded. How many people are going to first start typing immediately on this? No. You think, oh, it's just checking for messages now. Oh, it's doing that, it's doing that. And you're naturally going to give it some time to kind of finish its processing. But if the GUI shows up fast, which it would if you have a separate GPU on there, then you have the illusion that everything is running so much faster, which is kind of tricky in a GUI process. What if you don't have a GUI processing system? It's all command line. That trick's not going to work. So it's the operating system designer has to come up with these things to give the user the illusion that something is really happening. It looks like that. Well, a lot of people complain. They say, well, the Mac systems, they run so slow. Compared to well, that's because the average response rate on a Windows system, actually now they're about the same, but it used to be so much faster, significantly faster. So you booted up a Mac and this is so slow. Look at this. The whole thing is not even loaded yet. But the thing is, it would load in cache. So it loaded more initially. So when you ran it, and you might even still think about this. When you use a Windows program, you open it up. It goes into the ready queue. The process gets created. And then you close it. And it goes away. And the first thing Windows people have to learn when they switch to Mac, you start it, it never leaves memory. So it looks like it's gone. But you go back in, it's still loaded. Nothing ever really unloads until you stop it completely, or you force kill it and get rid of it. Once you start it, it just stays open, which is a different type of computing. But the memory is done. Well, the memory is managed differently, and the CPU schedule is managed differently. when you initially load it, it's going to take longer. But once it's loaded, it never goes out of memory. So like the Windows users, you load it up, you close your email program, well, you load it all back up. Takes longer. Close the email program, load it all back up. Mac system, you load it up once, takes a little bit longer than the average on the Windows stuff, but it doesn't go away. You don't keep loading it up again. It just stays there constantly. So the response time is faster on the second or third run versus every single time you're loading it fresh. Which is kind of interesting because people that go from Mac from PCs, that's their first thing. How do we close this? And they don't even know what they have opened up. And all of a sudden it's like, well, I thought I closed my email and my email is still running. So it's like, it's not minimized, but I shut the window, I closed the window. And then they start loading it up again. But it won't load up again, it's already loaded. So here's an example of the round robin with quantum time 20. And our jobs are 53, 17, 68, and 24. So it depends on the quantum time in terms of the average turnaround time. And so we have down here, unfortunately you can't see it, but it's pretty much giving you this scenario that on a 20, that job's going to finish, this job's barely going to finish. It probably should be higher to get the optimal time. So quantum time and the context switching time. The lower the quantum, the higher the context switching. So if the quantum here is 12, context switch is 0 if the process time is 10. Well, we have 2 quantums that we are wasting. So we have more idle. So this goes into your CPU utilization. So let's go back to CPU utilization for a second. We want to utilize the CPU 100% of the time, right? So it's constantly working. Well, if we have the quantum set at 12 and the process time only takes 10, then we have 2 break quantums. Well, the CPU is not being utilized during that time. So you can easily come up with CPU utilization using a round robin queue with a fixed quantum or even an averaged quantum, a calculated quantum. You're going to have less CPU utilization than if you had a first come, first serve. First come, first serve is going to take 10, 5, 1, 15, 10. It's just going to run it, and it's going to be having a higher CPU utilization score than this one will. Because we have 2 break minutes, 2 break quantums. So if the quantum is too high, low CPU utilization. If it's too low, high context switching, which is what? It's gonna raise, could possibly raise the response time, but it's definitely gonna raise the average wait time. Because you're gonna be waiting longer. You're not gonna finish as fast with a very low one because you have more context switching. So if it's 6 and quantum is 6 and the context switches is 1, because you have to do 6 and then another 6. So you're reducing the context switches. If you set it to 1, you got 9 context switches. That's pretty bad CPU utilization. Well, no, excuse me. That's a pretty long wait time. It's pretty good CPU utilization. You're constantly using the so CPU utilization is you're constantly using the CPU. This is very bad CPU because you have 2 non-utilization units. So that's how you're going to measure CPU utilization, by the way, when you do your calculations. Or let me say, that's one way of measuring it. That's the straightforward way of doing it. You could use time for a particular amount of time, and you can make up the time. You can use a counter for it, and how many jobs finished, and how many quantums did those jobs have or need, and then how much did we actually use the CPU during that time period. It's another way that you can actually do it. So the way that you calculate these numbers is going to be dependent upon what you're putting together. Long story short. So some students really like the idea of having the freedom, and other students go, oh, why don't you just tell me what you want me to do? I'm not going to tell you which 2 algorithms to compare. I'm not going to tell you what kind of jobs to compare it with. There's no set way of doing this. There's no mathematical calculation I can give you for any of the particular utilization. Oh, I see Joel in the hallway. So let me make sure this is a good stopping point for the attendance break. So let me pause the video here. Okay, so let me continue where I left off, and then we'll take another slight break soon when he comes back with the right roster. Okay, so the turnaround time varies with the quantum time because of what I was mentioning before and all of the factors that go into it. So the average turnaround time here goes up with the quantum time is 5. So and the other thing you can do is if you know the end result of what's going to happen, you could forecast. So you could say, if I'm building a scheduling algorithm, I'm trying to minimize the average turnaround time, and I don't really care about the CPU utilization. I could forecast an example and say, well, I don't want it to go above here, so I figure the happy medium, and then I set the quantum to match that, which is another approach they could possibly do. All right, so as I was mentioning before, most modern day systems do what's called a multi-level queue. And then if you have a multi-level queue, you can put multiple different scheduling algorithms on the different queues. And so then you can utilize the best of both worlds here. So the ready queue is partitioned into 2 separate queues, normally the foreground and the background queue. Are we ready? Okay. Oh. All right, let's get back to the lecture. Multi-level queues. Multi-level queues allow you to have multiple queues with multiple different algorithms that are assigned to them. Linux and Unix and Windows, everybody does multi-level because it's more efficient. As you mentioned, or as I hopefully gave you the impression earlier, the different scheduling algorithms have different pros and cons to them. So what might be good for some situation is really bad for others. So if you can create foreground, background processes or priority queues with different types of processes, then you can apply different algorithms to different situations depending upon the average characteristics of these situations. So if a particular type of job, you don't want to allow the same amount of scheduling time to it, as in this particular case, foreground versus background. So background processes are first come, first serve. They're running in batches because you're running it in a background. So you're not necessarily waiting for the input to come back. It doesn't really matter what order it runs in because we're not waiting for output. We're not waiting for user interactivity. It's not a user threaded activity. We don't care, so it actually runs faster in the long run. So it's actually, although background processing is not running with the most efficient algorithm, it actually serves its purpose better. As I was mentioning before, if we turned on our computer, we knew exactly what we were going to run. We're going to run it in that order. It didn't really matter. We were just waiting for it all to complete. Then that's a first come, first serve. That's the best algorithm to use. There's no context switching with that. It runs pretty fast that way. It makes better use CPU utilization as well. And then in the foreground, we can run a round robin, which means everyone gets some time. And then we go in a circle. We specify the average quantum or some kind of quantum time. And then we just round robin them all the way through so everybody runs simultaneously, essentially. So scheduling must be done between the queues as well to go from one scheduler to another. So you can have a fixed priority scheduler. So you can serve all of the foreground processes first and then run the background. If you do that, you get possible starvation. So if you have that, however, and the user goes home at night, all your background stuff is going to run while the user's not using it. So actually, this is what happens with most of your modern day operating systems with kernel level processes. Your backups, your I don't know, all of the CPU stuff that needs to get done will always happen when the user takes a break. So the more you use the computer, the more responsive it is. You turn your computer, you just let the screensaver come on, you go to lunch, you come back, and it's slower because all that background stuff's been running when you were gone. And so it has to switch back over to the foreground stuff that's been running. So that makes better use of the time, actually. So. And then we have time slice as well. So a time slice is what each queue gets a certain amount of CPU time. So by vocabulary again, a time slice is juggling between foreground and background queues in this particular example, where they're both sharing the same CPU. If you have multiple CPUs, you could schedule, I don't know if I go foreground, background, because background really is a low priority. But you could schedule and do a time slice between the two CPUs. But you'd have to switch between different queues that were getting different CPUs. So each queue gets a certain amount of CPU time, which is, it can schedule amongst its processes, or 80% to foreground in the round robin as an example, 20% to the background. So, meaning you're actually going to get 100% CPU utilization in the best world, perhaps, because you're shooting for 100% CPU utilization. But are you going to get 100%? Probably not. Especially if you do any context switching at all, you're not going to get 100%. It just doesn't happen that way. Multi-level queue scheduling. So you have high priority to low priority queues. You're going to do multi-level scheduling. So system processes are pretty high. Interactive processes are pretty high. Otherwise, it makes the system non-productive, non-responsive. Interactive editing processes, batch processes, and then down on the bottom we have student processes. Actually, if this were looking at a user mode, that students would be the user mode process. So it's going to be pretty low. User mode gets pretty low processing queues. Well, because if you think about it, if the system processes can't run, you have no system to run the user mode processes on. So the system level, kernel level, anything is always going to be a higher priority. So then we have multi-level feedback queues. So we can actually take to see what's going on. Look at aging systems. Look at the aging concept as well. And is starvation going on? And then use the feedback to adjust the queues. So this is a better modification. So a process can move between the different various queues. Aging can be implemented in this way. So we just automatically upgrade a process if it's been waiting too long. And then we have to decide, well, what's waiting too long? We can basically take the average time, calculate an average, and go, is it higher than the average? Is it lower than the average? But then calculating the average time is causing more aging as well at the same time. So you have to orchestrate the efforts. A multi-level feedback queue scheduler is defined by the following parameters. The number of queues, because it's multi-level. So how are you going to tier it? And then the scheduling algorithms that are going to be used for each one of the queues. So if you wanted to make your life more complicated, you can actually create a multi-level and then actually add feedback into it. Multi-level feedback queue for one of your comparisons. You don't have to do it that way. You could do shortest job first with first come, first serve if you wanted to. Or maybe round robin might be more interesting. Round robin, see, the more difficult you make the comparison, or the more difficult you make the implementation, the easier the comparison, because you have something to compare. If you take a first come, first serve with a last in, last come, first serve or something, then, well, actually you're going to cause starvation with that, but you're going to have different problems that are going to come out, and that's part of this exercise is to have you make you more aware about the different factors that go into the algorithm and why basically we don't have the perfect solution yet. No operating system really has a perfect solution at this point. So the method used to determine when to upgrade a process is also a factor. The method used to determine when to demote a process. And then the method used to determine which queue a process will enter when the process needs service. Which queue are you going to put it in, kind of thing. So here's an example of a multi-level feedback queue where we have three queues, Q0, 1, and 2. We have a round robin with a quantum time of 8 for the first one. And we're going to use a round robin with a 16 millisecond quantum time. And then let's just use the first come, first serve for the third one. The first come, first serve is not a bad algorithm. It's great for background processes. It really reduces all the processing time it takes for context switching. And then we have the scheduling. So a new job enters into Q0, which is serviced by first come, first serve. That's interesting. It's different from what's up here. And then it gains CPU time, and the job receives 8. This should say round robin. Q0 is a round robin, not a first come, first serve. Yeah, there's a typo on the slide here. And then it gains a CPU time, and the job receives 8 milliseconds from the round robin queue. If it doesn't finish after the 8 seconds, then the job is moved to Q1, where you're going to get longer time. That's actually automatic aging, because the longer it sits in the system, as it goes through the different queue levels, it's getting more quantum time. It's getting a higher priority of the CPU. because it's allowed now from 8 it moves to 16. If it doesn't complete at the first 16, we can move it to another one at 32 or something. We just keep doubling. You would just keep making it more effective, because it could be a really large process. If it is, then it goes way to the biggest one, and that's just going to run. So if job number 1, Q1 job is again serviced by first come first serve and receives 16, should be round robin anyway, then it still doesn't complete. It's preemptive and it moves to Q2, first come first serve. And then Q2, and then which one of the queues is running? That's the time slice. Which one of the time slice is which one of the queues is getting CPU time? So, and then the jobs inside are getting CPU time inside the queue. So here's our multi-level feedback queues, and the feedback is done for us automatically. What we don't want to do is keep running algorithms. We don't want to search and sort and do averages constantly. It's too computationally expensive, and it doesn't give us anything but busy work when it comes to those configurations. So here's a multi-level feedback queue, quantum 8, quantum 16, and then first come first serve. So a picture basically saying, you know, it could come out. If it's only 2, why make it all? Because I mean, usually students at this point will say, well, why don't we just make it all 100? You know, or make it all the biggest number possible. Then we have idle CPU time. That's not going to accomplish anything. Although here's the interesting phenomenon with that. The more idle your CPU is, the more battery life you get, and the cooler your computer runs. So you can actually tweak your battery life by making your CPU utilization lower. Which means, is your computer really running slower? No. Is the CPU still running at the same speed? Yeah, but your scheduler is making it so that your CPU doesn't have to work as hard. Depending upon what it's doing, it may not actually have to work as hard if all of it's doing is context switching. So bottom line, a CPU scheduler is really affecting the performance of your computer in general. So multiprocessor scheduling. Just like the multiple queues for time slices on one CPU, you can have multiple queues with multiple processors. Then you got a fast system, because you got process number 1, process number 2, process, well, 3, 4, about 4 is about as high as we go these days. Your average computer's probably only have 1 or 2 on it, but right now. But 2 is better than 1, as long as you have 2 separate processors. If you have a core duo, you know, do a duo anything, a dual, you know, it's all basically saying you have 1 processor with 2 chips. You want 2 different processors. So CPU scheduling is more complex with multiple CPUs are involved, because you have to figure out, well, which one are we going to use this one for, what are we going to use that for. And homogeneous processors with multiprocessors also exist. And then we have load sharing. And then we have asymmetric multiprocessing. So only one processor accesses the system data structure, alleviating the need for data sharing. Imagine if you have multiple processors and they're both working on the same job queue. You got corruption. Then you're going back to process synchronization techniques and all of the different scenarios that exist. And you're going to have one putting something into the queue, the other one taking something out of the queue, and you got the same job running on 2 different processors. It's like when the left hand doesn't talk to the right hand and you got 2 people doing the same work. It's just, it causes problems. So, what about real-time scheduling? So, hard real-time systems require a complete critical task within a guaranteed amount of time. Your microwave is a real-time processing. It's good. Yeah, it's not going to schedule jobs. There isn't. There's one job, another job. You press 10, start, it's going to start. It's going to run. Like I said, are there any other jobs in the system? How much time? Maybe we just only give it 5 and we're going to stop and do 5 again. Now, it's a totally different animal. It's easy, actually. Schedulers for that, there's no scheduling. Soft real-time requires the critical processors receive priority over less fortunate ones. That would be like a network attack. Are we going to keep searching to see if the ports are being attacked when one of them is being attacked right now? Nope, we're not going to keep around and look at. Instead, in a soft real-time, we're going to queue up so we can still look, but we're going to take care of one of them that's having a problem right now. And we're going to block it. We're going to do something with it. So we're going to run one process to handle a situation, and then we're going to keep our eyes out for multiple situations that might exist as well. thread scheduling. So processes are from the user mode, threads are for the kernel mode. So we could have multiple threads for one process, or we could have a one-to-one. Most systems these days are one-to-one mapping, one process to one kernel level thread. So one user mode to one kernel level. We can also have thread processing for the CPU time and scheduling. So local scheduling, how the thread library decides which thread is put onto the available. Well, it depends on how the scheduler and the processing, the lowest priority or the highest priority, in terms of what that thread belongs to. This isn't really done today. Instead, we think of thread processing just like thread scheduling just like process scheduling, because there's a one-to-one mapping. So when you start picking around the different mapping, you have the local versus the global scheduler, and you have all of the other things to worry about. How the kernel decides which kernel thread to run next as a global scheduler, because you have all these threads, they belong to multiple different processes, and you don't know, which it just complicates things completely. So if you have a one-to-one mapping, you don't have thread scheduling, you have process scheduling. Long story short. If you haven't done the first assignment yet, that pthread scheduling API, here's an example of how you would schedule the threads to run. Think of it as like process scheduling. So don't really need to cover threads because it's not really implemented, but here's some operating system examples. Solaris scheduling, Windows and Linux. So Solaris 2 scheduling, we have real-time system, and then we have interactive time sharing. So it spreads out and creates different classes or priorities of different types of processes that are running, and then applies different schedulers to it, depending upon what you're looking at. So we have priority on the threads, and the higher priority threads get scheduled first, essentially. So it's a multi-leveled higher priority to lower priority. And it's just a little example of the dispatch table as well. These operating system examples are old, like for example Windows XP. Now we're up to 8, I think, right now. So you don't actually have to know the differences between all of the different operating systems and how the CPU scheduling or the thread or process scheduling is working actually these days. Because CPU scheduling is process scheduling, if you think about it. It's scheduling the processes or the threads to get CPU time. Windows XP priorities, puts priorities. We have high and low priorities, depending upon if you're a kernel level or if you're a user level thread. And so we have different priority levels with different quantum times that are associated with it. In terms of Linux scheduling, it's based upon the two. We have time sharing and real time, two algorithms. And the time sharing, priority based, most people are using multi-leveled priority based algorithms. Credit subtraction here. Using a timer or an interrupt, essentially, to break it up. And actually, the one thing I probably forgot to mention, and I'll mention it now because I should have mentioned it earlier, the context switching is using interrupts. So the kernel will trigger a signal, which is a software level interrupt, to signal to the process to stop running, to start running, which is part of the context switching definition. So it uses an interrupt-based process synchronization mechanism to tell the processes to stop, which is the same library you use for the inter-process communication. You use the system call interface to create a mutex, or you use the mutex to create a signal, to use the kernel level facilities to control the processes from the user mode instead of from the kernel mode. Now, if you're doing a one process and from a user mode, and you have multiple threads that are created inside of that one process, because of the one-to-one mapping we have these days, it doesn't really matter. So people wonder, well, why in the world would you want to use a multi-threaded application then? Because in systems like Linux here, you may not necessarily have a one-to-one mapping. You have different priorities that are set, so you probably could get faster, and you probably do get faster processing with a multi-threaded application versus a single-threaded application. Because if you do create the multiple threads, you're going to have more processing being done per process because you have more threads. Because it takes that one process, turns it into 5 threads. those 5 threads are going to work faster because they're going to be, well, hopefully they're going to all get individual CPU time instead of one thread getting CPU time. So 5 of them will be getting CPU time instead now. So there's a compromise actually between, is it going to run faster? Well, if you threaded out your graphics and it went to a different processor, it's going to run a lot faster. So it depends on the design of the application. That doesn't mean every application out there needs to be a multi-threaded application to run faster. Some stuff probably won't run that fast, depending upon what it is. If you're opening up a lot of I/O, using a lot of stuff like that, then it makes sense to write a threaded application because you can send a thread off and it can be doing I/O, and the CPU and the I/O work simultaneously. So you get multiple stuff being done instead of it all going in one direction. So. And if you have multiple processors and you have multiple threads running, then that is going to be better too. So. All right, relationship between priorities and time slice. Depends on the configuration. So a lot of this stuff is kind of dated, so I'm going to kind of skip through it. Algorithm evaluation, deterministic modeling might take place. Queuing models come up. Implementation details come up in terms of this category. You don't have to know the algorithm evaluation for this course. What you want to be familiar with are some of the techniques that have been tried and used in terms of CPU scheduling and the criteria that I gave you in terms of how to compare the CPU schedulers. So that's, and I don't cover it in the slide set either, but that's pretty much the end of chapter 5, which was all on CPU scheduling. So if you have the book, it's not a bad chapter to read, because it's going to go over a couple more different variations that I have not covered. There's a little bit more different ways of combinations and different ways of putting things together. Also in the textbook there are some examples of the implementations. Just because the book says you have to implement it a certain way, you don't have to implement it that way. You can do it all in Java using your own implementation technique. You don't actually have to create threads inside of the process. You don't have to create a threaded application for this. You can do it any way you want. You're creating a simulation, and a simulation or a demonstration. The output can be command line as well. It can be anything you want. You don't have to show a graph or anything. It's not like a business class. So, questions about CPU scheduling? No. Questions about the assignments? I have a few more minutes to talk about it. No. All right. Well then, we are done for the operating systems class for today.